Hi guys, and welcome to Learn Extra Live Physical Science Grade 12's. Finally, it is your turn. As you can see, Phil is with me, and I feel silly saying how are you, Phil, because we've been here all day, haven't we?
Absolutely. And I'm great, thanks for asking.
Yeah, just in case the matrix wanted to know.
Sure.
Because I'm sure that they were wondering as well. So what are we going through in today's lesson?
Well, today we're getting into the second of 3 physics revision. Okay, now we're going to be revising the grade 11 part of your matric paper, so grade 11s you can probably follow as well. Some of the stuff might be beyond, but it's okay, you can see what's going on. So if grade 11s, if you're carrying on watching, keep on.
Yeah, deep breaths, guys. Okay, Phil, take your spot at the board, and I'll do my usual. Guys, don't forget to chat to us on facebook.com/learnextra. I'm also on Twitter @learnextra, and I'll be taking all of your questions. So anything that you are wondering and you need to ask Phil, come through me, post onto our Facebook page, tweet us, and let us know so we can get it answered. And don't forget, we also give away these awesome Casio calculators to those mindsetters who always post on the page, whether they're asking questions, putting inspirational quotes, posting pictures, anything really. It's just the interaction that counts. And before we get started, I want to say big up to Liberty. Thanks to you guys. You make this awesome show possible. And we just wanted to let you know that mindsetters really, really do appreciate you sponsoring this awesome show. Now, without taking any more time from your lesson, Phil, take it away.
Thank you so much, Indy. Okay, so what I've been doing over the last 2 weeks or so is we've been starting to take a look at last year's final papers and actually breaking them down and trying to get a sense for what's actually going on inside these. So we covered questions 2 and 3 last week. We're going to be doing 3, 4, 5. And what I've actually done is I've sent through a few things to Indy, and I hope that you got them. But
I'll let you know shortly.
Okay, it's a little packet of questions for you guys.
And I got them.
Absolutely, fantastic.
Yay!
Okay, so she's going to post them up on your Facebook page in a little gallery all together, and you guys can put them all together and actually start answering and start discussing them as I go through them. So unfortunately, the writing is a little bit small on the screen, but I can't actually make last year's exam any smaller, unfortunately for you guys. So what I'm actually going to ask you to do is actually follow through with me on each question. So we're going to be doing questions 4, 5, and 6, and there's some pictures going up on Facebook in a short while. But while you wait for that to happen, we're going to start taking a look at the questions. Okay, question 4 was a relative motion question. Now, even using grade 10 reasoning, you can actually start to work out what's going on inside here. But it's quite tricky. So what I want to do is I want to slowly break this down and slowly work through this with you and see what goes on. Okay, so now I've left myself a lot of space to work out because I'm going to need it. Okay, now let's get started into it. Okay. I've got a patrol car which is moving on a straight horizontal road at a velocity. Okay, so now here's our object, a patrol car, okay, which is going to be titled P, I think, later on inside the question. So patrol car is moving at a velocity of 10 meters per second east. Very important because this is a vector and vectors have directions. Okay, at the same time, a thief in a car ahead of him. Okay, so there's a thief in a car. So that's going to be referred to as T a little bit later on. Ahead of him is driving at a velocity of 40 meters per second. Okay, right, in the same direction, so also east. Okay, so now they later on tell me, after drawing a really nice picture for me, that velocity of, now when they say VPG, that means the velocity of the patrol car relative to the ground. Okay, so there we go. So there's the P. There's the G, okay, and then T for thief, and then G for ground. So they've given me 2 different velocities. Now we're trying to work out something a little bit later on in terms of relative velocities. I'm going to show you how to work with this. Okay, so they've told me that the velocity of the patrol car relative to the ground is 10 meters per second. There it is. So there is my one velocity. Okay, the velocity of the thief's car relative to the ground is 40 meters per second. So what they're asking for is write down the velocity of the thief's car relative to the patrol car. Okay, so now I'm just going to put something on my diagram which might actually help me out a little bit, is that is the direction of east. They are both driving east. Okay, the thief is driving at 40 meters per second. The patrol car is moving at 10 meters per second. Okay, now we're trying to get a relative velocity. Okay, so we're looking for the thief's car relative to the patrol car. So what we're actually looking for is velocity of t relative to p. Okay, now in order to do that, what I've actually got to do is use these two other velocities in order to get from t to p. So what I'm going to do, because they're both in the same direction, is I'm actually going to compare them. We've got to find out, in terms of relative, there is a difference between these two. The difference between 40 and 10, because they're in the same direction. Now, just for reference sake, I'm going to choose east as a positive direction. It's quite important to note which direction is positive, because that's important. Okay, so now I've got east, I've got positive 40 meters per second for my thief, I've got positive 10 meters per second for the patrol car, and what I've got is all the information which I need to get the remaining answer. So what I'm going to do now is I'm going to try get from t through to p. So this is how you set up a relative velocity questions answer. Okay, so now it's all about the lettering. So I'm looking for v t relative to p, so thief relative to patrol car. So what I'm going to do is I'm going to get the difference between their two velocities. This is how you get relative. Relative is a comparison. It's a difference between the two. So what I'm going to do is I'm going to take v of tg. Now this is all going to make sense once I actually highlight the important pieces, minus v of pg. Now what this does for me is it allows me a way of getting, and this is how to set this up properly, these outside two letters. Okay? What actually starts to happen is that I'm comparing them both to the ground, okay? And that allows me to get rid of the ground. So what you'll notice is that the ground, because you're subtracting, this is the way I think of it, is we'll get rid of that common thing. And let's substitute in our values, let's see what we get, and let's take a look at our answer. So now if I substitute tg is positive 40 meters per second. Now I'm putting in a plus just to emphasize that he's going east. Subtract from that the positive pg, which is patrol car relative to ground. I get positive 30 meters per second. Now, because I get positive, I can apply a direction. And please, I've noticed even in my matric, sometimes they leave off the directions and it's a silly way to lose marks. I'm going to say that it's 30 meters east. Okay, now, just for reference sake, they can always ask it the other way around. The patrol car relative to the thief, and what you'll actually notice is that your answer comes out to be a minus 30. So the patrol car relative to the thief would actually be going in the opposite direction. If you were sitting inside that thief's car, you would actually see the patrol car going in the opposite direction. Okay, now, here's where things get interesting. So it says a person in the patrol car fires a bullet at the thief's car. So you can actually see inside the car there's a policeman, and the policeman has got his gun drawn and is shooting a bullet towards the thief. He's trying to stop the thief. Okay, the bullet leaves the gun with an initial horizontal velocity of 100 meters per second relative to the patrol car. Okay, so relative to the patrol car. Ignore the effects of friction. Now, I've got to write down the initial velocity of the bullet relative to the thief's car. Now that one's quite difficult. What I've got to remember is that the thief is actually starting to move forward. So we've got a thief which is traveling forwards, and we've got this patrol car. Now why am I being told all these different velocities? Well, one of the things is that I've got the velocity of the thief relative to the police car. Now, if I start to take a look at another object, which is the bullet, okay, right, the bullet relative to the patrol car. Let's see if this method actually works out. Okay, so now I've got V of BP. Now this is starting to get very complicated. We've got V of BP. Now what I'm trying to get is the initial velocity of the bullet relative to the thief's car. So I'm looking for bullets relative to thief. So BT. Okay? So that is the question mark. Now what you've got to realize is that VBP is 100 meters per second. So that is 100 meters per second. But we've also got a relative velocity of this thief's car of 30 meters per second. So what's going to happen is that this car is actually running away from the bullet, and that means that the bullet reaches that car in a slower time. So what I'm going to notice is that the relative velocity that I'm actually finding is going to be less than it was before. So what we're going to do now is we are going to calculate the velocity of the bullet relative to the thief. So what we're going to do is we're going to do a comparison between two velocities. Now we've got to decide which velocities we're going to use. So what I'm going to use is bullet relative to patrol car, and then to get rid of the patrol car and what we've got to do here, sorry, I'm getting tongue twisted here. Okay, and we've got another velocity here which we can actually use, which is VTP. Now I want you to notice that the same letter happens in both of these. That gets rid of the patrol car out of this situation and leaves behind B and T. This is how this works. So I've got a positive 100 meters per second, minus from there, what else? Positive 30. And what we'll find is that there is a positive velocity of 70 meters per second. It's positive, so therefore it is still east. So I hope that you understand what's going on there and how to work out relative velocities. Okay, you've got to get a positive direction first of all, and then start to set up your sum to eliminate the object which you don't want. Okay, I hope that's quite clear and that you've answered 4.1 and 4.2. What's happening on the page there, India? I can see you sort of feverishly typing away.
Always, always. Let me have a look. There's no questions as of yet, which is good because it means that hopefully everyone's understanding. Guys, if you aren't understanding, please post questions onto our page. Let me quickly give you a recap of how to do that. Facebook.com/learnextra. You can also chat to me at learnextra on Twitter. And Ashworth says, hi, Indy, hi, Phil, and hi, Mindsetters. So I hope you grade 12s are enjoying the show immensely.
Great. Okay, well, thank you very much, Indy.
Pleasure.
So what we're going to start doing is I'm actually going to skip a small piece of question 4 and come back to it a little bit later on in the show because we've actually practiced lots of them. Now, that's a conservation momentum one. Now, one of the ones which I've found very, very badly answered is actually question 5. Question 5 during the exams in terms of your Newton stuff is terrible. Please, guys, you've actually got to learn how to answer these. Go back through grade 11. Go through your Newton 1, 2, and 3. Okay, now we've got this rescue helicopter which is stationary above a soldier. So I'm just going to highlight the important pieces of information and let's see what goes on. So stationary above a soldier, the soldier of mass 80 kilograms, so that's quite important, we need to know his mass, is lifted vertically upwards through a height of 20 meters. Okay, so there we've got a displacement by a cable at a constant speed. Now there's a very good reason that they've made this in capital letters. A constant speed. Now, I'm not even going to go any further. What I've got to do is I've got to realize this. At a constant speed, I've got to realize that F net equals 0. Now, you might say, how on earth did you know that? A constant speed means that there is equilibrium. Let me repeat that. Constant speed means equilibrium. It means that there is no acceleration. No acceleration means that there cannot be a net force. Net force makes acceleration, and there is none. Please, a constant speed means that there is no F net. F net equals 0 newtons. Now, what they have told us is what that constant velocity actually is, and that's quite handy. The tension in the cable is 960 newtons. Assume that there is no sideways motion during the lift. Air friction is not to be ignored. Now that's quite interesting. That means that friction must play an important role. Okay, now I've got to go through my very, very basic stuff. They've asked me to state the work-energy theorem in words. Okay, and I think we have time for 1 or 2 questions before we go through to the first ad break, so let's get into this as fast as we can. Now the work-energy theorem in words. Now, if you can't remember how to say out a definition in full, write down its equation and see if you can say what that equation says. Okay, so the work-energy theorem says that the change in an object's kinetic energy is equal to the work done by the net force. Let me repeat that again. the change in kinetic energy of an object, and that's that part, and you've just read out what delta Ek actually means. So some of you might see it as just delta capital K is equal to work net. Both of these are the work energy theorem. Okay? So basically the change in kinetic energy of an object, now this is such easy marks, look at them. There's 2 marks staring you there right in the face. The change in an object's kinetic energy, there's the first mark, is equal to the work done by the net force on this object. That's really, really important. I need to know the change in Ek, I need to know the work done by the net force. Really not too difficult, I hope that you managed to follow that. Now, I'm going to show you where lots of people lose marks in the second one. They want me to draw a labeled free body diagram. Now I'm busy rubbing it out instead of highlighting it, so let's do that instead. Okay, so a free body diagram showing all the forces acting on the soldier while being lifted upwards. Now that's a little bit of a challenge. I've got to put in proper labels, and I'm going to show you how to give a proper label for a free body diagram and what is different from a force diagram. Free body diagrams and force diagrams kind of look similar. They've got arrows of the same size pointing in the same direction, but those arrows are arranged in a slightly different way. So a free body diagram itself, a free body diagram starts off with a dot in the middle. So what we've got to do is we've got to realize is that there are forces acting on this person. Okay, so we're trying to find acting on the soldier. So now all of our forces labels will end in on the soldier, force of something on the soldier. So let's start to take a look at what is happening inside the question. He's being lifted upwards with an applied force of 960 coming from the helicopter. So if you are given the value, write it on, so 960 newtons, so 960 newtons, and my label, please, the label must say, so I can say helicopter on soldier. But that is not a proper label. I have to say force of. So force of helicopter, so where's the force coming from and what is it acting on? So force of helicopter on soldier. Now that is a full label. Now your examiners might be a little bit more lenient, but that is the proper way to label a force. Force of something on something. Now if you've got one object and you should have in a force or a free body diagram, the forces should all be on the same object. Please be certain of that. Now there's a couple of other forces which other people have forgotten about. Okay? Now, these two forces must add up to the same force as that. How on earth did I know that that was the case? Now we're told that there is a constant velocity. That means that force up is equal to force down. That's the secret weapon I've got. I know that because of constant speed is that the force up and the forces down must actually be in balance. Now, please let's just take a look here. I've got two places where force comes from. There's a mass and there is air friction. There we go. Okay, it's quite important that we know that there are two forces in here. Now, mass itself is not a force, but it results in one. So I've got a force downwards, and that is called gravity. Gravity is always acting on objects. So force of gravity on soldier. Now we can even calculate it if we really want to, but they just want labels. Okay, so force of gravity on soldier. Okay, and there is another small force as well that I must not forget. There is a second force. Notice how I'm putting all the forces with their tails on the center point, and that is what makes a free body diagram. All the arrows begin in the middle. They cannot point inwards to the object. So this last one is friction. So friction on our soldier. So there is a force of friction acting on that soldier. Okay, all right. Unfortunately, I think it's time for our first ad break.
Oh,
I always
sad
get
for
sad.
sad for Phil. Lucky for me because I get to talk again. Yay! I love it's my favorite part. Yay! Okay, grade 12s. I also have to tell you something very very important, which is just for you. We've got spring school coming up, which starts on the 1st of October until the 7th, and what that means is some intensive training and revision where we really get you ready for those finals. Also, I have a very, very important announcement to make, or something I have to say. Now, this is to a birthday girl. This is to Fendi Dulo. Lady, please let me know. I'm so bad with names. Maybe I'll even get one of I'll get my producer to teach me during the break. And she is finally 18, so I have to say happy, happy birthday to you. And on that note, let's take a break. See you now. Hi guys, and welcome back to Learn Extra Live Matrix. I hope that you are enjoying this lesson and you are having lots of fun learning more and learning extra. Okay, so now I got a post from Ashworth, and Ashworth posted the 3 C's of living life, which I thought would be really good to read out to you guys. And thank you, Mindset, for posting such encouraging and inspiring words onto our Facebook page. So now the 3 C's in life are choice, chance, and change. You must make the choice to take the chance if you want anything in life to change. So I thought that was really, really cool mindset, and thank you so much for posting that. I do have, okay, Pendulo, I'm sorry for getting your name wrong. Happy birthday again, lady, and you're now 18, and I hope you have the greatest day ever. Also, I wanted to make sure that you guys do remember that we are giving away a Casio calculator, as well as a labeler. And with this fancy labeler, you get to label everything from your space case to your school bag to anything. So all you have to do to win that is to post onto our page and to either post a question, an inspirational quote, maybe even help another mindsetter out, and you could stand a chance to win that awesome Casio calculator. Grade 12s, this is very important. If you have a look at our Facebook page, you'll see that we have redone the top timeline, especially for you, starting from the 1st of October to the 7th. We've got spring school, which is coming up, and I will be posting a link onto our Facebook page where you can download the schedules as well as the spring school books, and I'm sure you guys have all been seeing that little ad with Kaklejo. And what you can do is you can either order the spring books or you can download them. And I see Phil's getting all tetchy because he's like, I want to teach, okay? Phil, you teach. You do what you do best.
Thank you so much, Indy.
Pleasure.
Okay, all right. So question 5, we're into the thick of it. We've got a fully labeled free body diagram. Please, this is not a force diagram. Free body diagram starts with a little center in the middle, and all the forces go out. Okay, now let's get stuck into this. Now, it says 5.3. Now, 5.3 is something which I saw was answered so badly. So it says write down the name of a non-contact. So that means not touching force that acts on the soldier during the upward lift. So this is a bit of a clue. It's a force which doesn't actually touch the soldier. Okay, so I'm getting a bit tongue-tied here. Okay, so there's a soldier and there's a force which doesn't actually need to touch him to act on him. Now, there's only one of these 3 which doesn't actually need to touch him directly. Now, friction is due to touching. The helicopter is definitely touching him because he's got a rope. What about the force of gravity on the soldier? So 5.3 is easy enough. What I'll actually find is that 5.3 itself is gravity. And gravity is the non-contact force which is acting on him. So I'm hoping that everything's going all right and you guys are getting on the page and you're busy following us very nicely. How are they doing, Indy?
They are doing very well.
Fantastic. Okay, so question 4.5. Now this, 5.4. I'm getting everything muddled up today. Okay, it says use the work energy theorem. Now, please, one of the major problems that I actually find with these things is that people don't actually use the method that's actually needed. So the work energy theorem, I've got to use the work energy theorem in order to be able to do this, to calculate the work done on the soldier by friction. So we are looking for work done by friction. Now, one of the things that I've got to start with, and please, 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 guys, make sure that you're actually doing this, is that you start using the work energy theorem in the first step. You can only use the work energy theorem. You can't invent your own ways. They will subtract marks. So what I'm going to do is we're going to use the work energy theorem to calculate the work done on the soldier by friction after moving. Okay, we're getting into it. After moving through the height of 20 meters, let me show you how to do this. Guys, it's actually really not that hard. I'm going to show you 2 different ways of doing this, and both of them are correct. Okay, now the work energy theorem says the following. It says that work done by the net force is equal to the change in kinetic energy of the object. Now, it could be delta K or delta EK. It doesn't matter which one. So sometimes you might actually say that it's delta K. Really doesn't matter. Okay, now what I've got to be able to do is I've actually got to be able to work with the left and the right-hand side of this. Okay, now the really, really cool thing about this is I can actually take a look at this right-hand part and do something quite clever. It tells me during the question that there is constant velocity. Now, if you're quite smart, and I hope you are, if you're in matric science, I think you are quite smart. Delta EK relies on a change in velocity. If there is no change in velocity, that is 0. So this is magic. One of the reasons that this is 0 is because of constant velocity. Okay, now that's one of the big breakthroughs in this. So constant velocity is the reason that delta EK is equal to 0. Constant velocity tells me that the EK is not changing. Okay. Now let's get into work net. Now work net is made up of various parts. It's work done by the individual forces all added up together. So let's do this together. Okay, so work net is equal to the work done by the helicopter. So I'm actually going to label it work done by the helicopter. That's the applied force. Plus work done by gravity. Plus work done by the friction. Now we're going to work with these separately. Now we've got information about the work done by the helicopter. We've got information about the work done by gravity. And that leaves us only with work done by the frictional force. So all I've got to do is I've got to figure out how to figure that out, add it all together with my lovely, fantastic Casio calculator. We're going to do this together, and I'm going to show you how it all comes out. Okay, so now work done by the helicopter. Just remember that anytime you've got work, it's equal to the force from the helicopter, which we were given, multiplied by the change in displacement. Now, because this is vertical, I'm going to say that it's y, times by cos of the angle. Now, remember that the angle that's going to come is the angle between the displacement and the force. Now, the soldier is moving up, the helicopter is moving up, and the force is up. Do you agree that because we're moving up and the force is up, the angle here is 0? So that is cos 0. Now the next part. Now we're going to deal with gravity. So the force of gravity multiplied by the change in displacement multiplied by, now here you've got to be very careful. Cos of, well, now I've got to decide. My force of gravity is down, but my displacement is up. Now if you see my 2 fingers are 180 degrees away from each other. So just a reminder is that my movement is up, my gravity is down. So this angle between them is actually 180. Very, very tricky. Plus work friction is equal to 0. Okay, from here on in, it's so easy. All I've got to do is substitute in. Okay, one of the tricks is that I've got to remember is that my cos already changes these things into components. You don't have to put in positive or negative forces. Please, just a reminder that these forces are just put in as scalar quantities, even though they're not, because my cos will give things direction. My cos makes things plus or minus. You don't put in your force as a plus or minus, because sometimes that's a mistake. This is purely the magnitude of the force. Cos gives it the direction, the plus or the minus. Okay, so now let's start talking about my helicopter. The force of the helicopter was 960 newtons upwards. Displacement was 20 meters. Cos of 0 is just 1. So there we go. Plus my force of gravity. Now I've got to be very careful about the force of gravity. My force of gravity is 9.8 multiplied by the soldier's mass, which is 80, multiplied by 20. Cos of 180 is -1. There we go. Whoops, we're not on time for an equals. We're almost there. I'm getting a little bit eager. So there we go. And we're almost there. Okay, so let's put this all into our calculator. Let's see what comes out. Now, please don't go solve and write down and resolve. You can do this all inside your trusty calculator. Let's make some space. Let's put it all in and let's see what comes out. So I've got, open brackets, 960 multiplied by 20. So there we go, 20. Okay, we don't need to multiply by 1. So then we've got inside the next brackets 9.8 multiplied by 80. Next brackets 20, so that 20 meters displacement multiplied by -1. The -1 came from the cos of 180. Let's put it all together. What I get is 3520. There we go. So 3520. Okay, plus work on friction is equal to 0. Now all I have to do is move it across. So work on friction is equal to -3520. And let's just double check that we've written down the correct amount. 3520, it is joules. Now, you can have negative work. What that means is that this type of work is taking energy away from the object. Just a reminder that negative work is work which takes away the total amount of energy of that object. So now the reason behind this is because friction is acting against my displacement. Just a definition for negative work is it's work which reduces the energy of the object, and it's also work which is done by a force which is acting against the displacement. So friction is definitely always acting against my displacement, and that is why this is a negative form of work. Now, what I wanted to do was do this in a slightly different way. Now, we absolutely can do this in a different way. What I'm going to do is I'm going to redraw our force diagram. Now, our force diagram, sorry, this is a free body diagram. I'm getting them mixed up. Comprises of 3 different forces. I've got frictional force, I've got force gravity, which is equal to 9.8 multiplied by 80. Now, this is a separate way of doing things. So that is 80, not 10. Let's just make sure that we get this right if you're taking notes at home. Now, this is a different way of using the work energy theorem, which is also correct. I know that the force of the helicopter is equal to 960. What you can actually do is you can work with F net as well. So what I'm actually going to do is I'm going to start out with work net is equal to a change in EK, which once again is still equal to 0. So I'm solving the same question doing a slightly different way. Work net is made up of F net multiplied by delta y cos, and because we've got absolutely no difference between the force which is applied, or my net force, and my displacement, that will be cos 0, so we don't need to make it a negative. Okay, so let's work through to our force net, and let's actually work backwards from it. Okay, so F net multiplied by my displacement of 20 multiplied by cos of 0, which is 1. Okay, what I'll actually find here is that F net itself, remember I said this right in the beginning, F net is equal to 0. Now I can work with this. I started off from my work energy theorem, and what we're going to do now is we're actually going to find a force of friction and get through to work on friction that way. Now F net is made up of all these forces added up, some of them positive, some of them negative. Now here you would have to substitute. I'm going to choose a positive direction as up. Okay, so now what we're going to do is we're now going to add up our forces to get F net. So I've got force of heli plus the force of gravity plus the frictional force is equal to 0. Now my force of heli was a positive force, which was positive 960, plus a force of gravity, which is going to be a negative 1. So what we're going to do is we're going to say negative 9.8 times by 80. Okay? And what we're going to find is actually how much my frictional force is. Okay? So what we can do is we can take our 960 and we can add all this together. So now this is a slightly different way of doing things. You don't have to do it this way, but it's just an alternative because I'd like to work with Newton's laws. Okay, so 960 plus, and inside the brackets I've got negative 9.8 multiplied by 80, and out comes my answer there, so 176. So what I'm going to find here is that friction is a negative force of 176 newtons. Now I'm not done yet. They wanted the work done by friction. So work done by friction is equal to F of friction, my displacement, and my cos of, and remember that friction is acting against displacement. So it's generally 180 degrees apart from it. So let's substitute in my values. Okay, now just a reminder that when you substitute into this formula, you just take the value, you don't keep the sign. So that is just 176, because the cos will add a direction to it. Okay, my displacement of 20, and then cos of 180, which will give me negative 1, and we will get exactly the same as we did before. We will get our total work done by friction as 3520. And that is a different way of doing exactly the same thing. And sadly, it looks like we're running into these ad breaks again.
No, can't be.
It's the second one, but unfortunately, we need to give these guys and myself a break. I think I've got a frog in my throat.
You got a frog in your throat. Okay, guys, I see we've got a few questions coming through on the page. I'll go through them with Phil, and maybe if they're quick, I'll get him to answer them straight after the break. And now I'm dropping everything in studio. That means it's time for a break. Hi guys, and welcome back to Learn Extra Live. This is the last 15 minutes of the show. Now, Sofiso said to me on the page, he said, Indy, nice to see you taking the lesson seriously by doing it practically. And what he was talking about is me dropping this awesome labeler off my table. So now what Phil and I were talking about, we thought, you know what? We might as well just give you a quick competition question just to see. And you know what? Phil's going to give me the answer, and whoever gets the question right first will win this Casio labeler. What do you think, Phil?
I think that's a great idea.
Okay,
well, guys, pens and paper quickly. Labeler's up for grabs, hey?
Labeler is up for grabs.
Sure, that labeler is awesome.
First correct answer wins.
Great.
That's posted on the page.
Okay, well, guys, it's coming to you quick and fast. You better draw this down. Now, what I am going to tell you is that the labeler fell from rest from a height of 1 meter on the table down to the floor. What is its final velocity as it strikes the floor? If you find that velocity, the first correct answer, you guys get the labeler. So let me just repeat those important facts. Fell from rest, down 1 meter down to the floor. Guys, go for it. Try and calculate that for me. A little bit of physics challenge, and I'm hoping to see some answers in the next 30 or so seconds. You guys must be quick on this one, otherwise it's going to be gone. Okay, for the rest of you that are not into kinematics, what we're going to do is we're going to go into question 6 of the November paper last year. And this is one of my favorite sections because it's one which you can absolutely cream. You guys can get the marks out of this so easily. Let me show you what I mean. So I've got a train approaching a station at a constant speed of 20 meters per second. There it is. So 20 meters per second with its whistle blowing. So it's making some noise, and the frequency of the noise here is 458 hertz. An observer standing on the platform hears a change in pitch. Here we go. A change in pitch. Now that's quite important. That means a change in frequency as the train approaches him and passes him and moves away from him. Name the phenomenon that explains the change in pitch heard by the observer. Now this one is so easy. Please, the change in frequency because of moving objects. There we go. That is called Doppler. And this is the Doppler Effect. And there's going to be a question about this. There will be one in every paper. Look for one in your final papers. The Doppler equation is going to come up. It's guaranteed, and it's inside this one as well. Okay, so it says calculate the frequency of the sound that the observer hears while the train is approaching him. Okay, that's quite important. We're going to need a diagram for that one. Use the speed of sound in air as 340 meters per second. Okay, grade 12s, there is no excuse for misusing the Doppler equation. Now, what I'm going to do is I'm going to show you a few tricks on how to use it. First, we're going to start with the full equation. I'm going to show you how to make it a little bit simpler. So the frequency of the listener is equal to V plus or minus. Now, the plus or minus is what gets everyone. and then VL at the top, and then VS down at the bottom. There we go. And then this is all in brackets, and we multiply by the frequency of the source. Okay, before we get anywhere, what I'm going to do is I'm going to fill in the information which I already know, and then I'm going to show you how to use the plus and the minus correctly. First of all, I need to make a prediction. That is a step one of my Doppler. I need to predict, is the frequency going to go up or is the frequency going to go down? I expect that the frequency, when the two are coming close together because the waves are being squashed, frequency increases. There we go. So frequency is going to increase. Guys, it's really not too bad. All you got to know is that if two objects are getting closer, the frequency is going to be increased. Okay, so I need to keep that in mind as I play around with my formula. So let's go straight to the substitution. Let's try to figure out what's going on. V is the velocity of the waves. Now, there might be light waves, there might be sound waves, and that's what they are in this question. And we got told that the velocity of the sound waves was 340 meters per second. So there it is, V in both positions. Now, at the top, the listener or observer is not moving, so the plus and minus doesn't really matter there because that's 0. At the bottom, I know that the source of the sound is changing. Now, I've got to choose a plus or minus which agrees with my initial prediction. Okay, now, when I say the frequency is increased, that means that what goes inside that bracket must be larger than 1. Now, you've got to think of this like a fraction. How do you change the bottom of a fraction to make the fraction bigger? So let me say that again. The denominator, the smaller part's usually at the bottom. Now, how do I change that so that the whole fraction increases in size? How do you change a denominator to make the fraction larger? You make it smaller. You make the denominator smaller. So what I'm going to do is, because of my prediction, I take away from the denominator, because what's going to happen is that fraction is now going to be larger than 1. Because I took away from the bottom, the whole fraction will increase, and that's what I'm trying to do to the frequency. So now all we need to do is we need to put in the original frequency, and the original frequency here was 458 hertz. So there we go, 458 hertz. Now, it doesn't matter if you get the plus or minus wrong, because it's as easy as changing it. Okay, now I'm going to show you just how awesome this calculator is in a moment, because we're going to put this in and I'm going to change it from back to forth to back to forth, and we're going to try and see what's actually going on. Okay, we can put the whole Doppler equation inside this calculator. So now 340, you can't put in a plus or minus, but it's 0. But if I say 340 and I push a fraction button, that makes a lovely fraction over there. Okay, now I'm going to put in 340 minus 20 on the bottom. So there's the whole Doppler equation there. Now all I've got to do is I've got to put this whole thing into brackets, so let's do that. We should have done that right in the beginning. But this is the great thing about this calculator, is I can go back and do things anytime. There we go. There's my brackets. So inside brackets next to it, I've got to put my 458. So I hope you can see everything, 458, and out comes the frequency. All I've got to do now is press an S to D button over here, and the S to D button will get me my answer. So I get an answer of 486.63. So I'm just going to round that, 486.63. So 486.6, sorry, let's just make sure that my hand is listening to my brain. So 486.63, don't forget your unit, hertz. Okay, now what I'm going to do is I'm going to show you on the calculator just how easy it is to experiment using the Doppler equation. Now, what if I didn't know if it was plus or minus? All I need to do is I need to go back to my equation, delete the minus, and add in a plus. So let's see what that gives us once we've done all of this. I get a frequency which is now lower, and I know that that can't be the case, grade 12s. I made a prediction that the frequency must be higher than before, and this one is wrong. So I know that it's not plus 20 down at the bottom. So even by doing a proper prediction, I know that I have to change that to a minus. If you did it the wrong way around, push my equals and my S to D button. There we go, 486.63, and there is my answer. Does it agree with my prediction? Absolutely. that means that we're most likely correct, and that's 4 marks. And it's going to be in your exam, guaranteed. Okay, now 6.3 says, how will the observed frequency change as the train passes and moves away from the observer? So now they're moving further apart. Now what we've got to do is we've got to select the correct answer. Write down only increases, decreases, or remains the same. Well, now, if they were approaching, the frequency would be higher. And if they're going away, the frequency is going to be lower. So this one's actually really, really easy. All I've got to do is I've got to say for 1 mark, decreases. Okay, now 6.4. How will the frequency observed by the train driver compare to the sound waves emitted by the whistle? Okay, now what we've got to do is we've got to talk about the frequency observed by the train driver. Remember that the train driver is on the train. Okay, compare that to the sound waves emitted by the whistle. Now the train driver is moving with the train and they're going together. There is no difference in their velocities. Now there's the clue. There's no difference in the velocities between the listener and the source. If there is no difference between the listener and the source, what you'll find is that you'll add and subtract the same number. And that means that we're going to have equal to. Now, if you've got a train driver which is sitting on a train, we're going to find that he has exactly the same frequency observed. Now, it's going to be equal to. That was the answer there. Now, the reasoning behind that is actually quite easy. So, equal to. You only get Doppler when there's a difference in velocities between your 2 objects. Now, because the train driver is moving with the train, what we're going to find is that the velocity of train driver is the same as the velocity of the train. So velocity of driver is the same as the velocity of the train. Same as train. Okay? So really, really, really nicely done. Let me just go through that again. Okay? Now, I've got to remember that Doppler is going to come up every single time I write a physics exam. We're always going to be asked to compare velocities. We can do velocities, all sorts of things. One thing which I haven't seen is they haven't combined a relative velocity with a Doppler one, but they've told us that generally you will only get one moving object, so either the listener or the source which is going to be moving. Okay? So now what I want you to do is I actually want you to practice through your Doppler equation. Practice with the plus or minuses to see that you get your prediction right. So step 1 is always your prediction. Step 2 is your equation. Don't reach for your equation straight away. It's going to hurt you. Make a prediction first. You don't even need to write it down. So over here we saw that the train was approaching the man. So the part that fits between these brackets needs to get smaller at the bottom to make the whole fraction bigger. One of the reasons that the fraction needs to get bigger is because the frequency needs to get bigger. That was to do with our prediction. Prediction is always the most important step. Now, I've got a few minutes left, and I'm going to ask Indy, are there any pressing questions?
Well, the only pressing question right now is what the answer is for the labeler, the falling labeler.
Oh, okay.
But let me have a look. Let me just have a quick
Do you
little
want me to
squiz.
work through it with them to put the others out of their misery?
Yeah, I think so. We did have a question earlier. I think that was kind of along the same lines. Maybe we can.
I did think that we answered that along the way. I think we should answer the challenge.
Yes, definitely.
Okay.
Definitely.
All right, guys. Okay, the Casio labeler challenge. Let's actually do it up. Let's put it up on the board. I'm going to take you through a little bit of kinematics because I haven't done that in a little while. So we had our question. So we had Indy sitting there, and we had our labeler. The labeler started with an initial velocity of 0 meters per second. That was the first hint which I gave you. It fell down to the floor. The floor was 1 meter away. That was another piece of information. So always when I've got these diagrams, it's the first thing that you should do in physics is always draw yourself a diagram. Choose yourself a positive direction. Now I've got a diagram, a direction, so those are the 2Ds which I must start with, and then a table. No equations yet, so what I do is I say VVT, because I've got 2 V's and then TAY. If it's on a flat surface, it's VVTax. Okay, let's put in the information which I know, and then we can select an appropriate equation. And then Indy's going to start hunting around on the page and giving somebody a labeler.
Oh, yeah.
So we've got a V initial of 0 meters per second. Our physics in action, we are looking for the final velocity. The time we don't know, we don't care either. I didn't ask you for that. The acceleration, a lot of you are saying, okay, well, we don't know the acceleration. Yes, you do. This object is in free fall. That means that the acceleration is 8 meters per second squared. Down to the ground, my displacement is 1 meter. Okay, now there is only one equation that you guys have got that doesn't involve time. Now, that one is the one that follows. So if I say VF squared, now you guys are busy working with me that you didn't solve this earlier. Okay, plus 2a delta y. So let's put this all in. So V initial, 0 squared, plus 2 times 9.8 multiplied by a displacement of 1. Okay, what I'm going to find is, that's 19.6. I hope my mental maths is right. We can double check ourselves on our awesome calculator here. So 9.8 multiplied by 2, absolutely. All right, we're getting there. 19.6 is not our answer. Just remember that our answer must be square rooted. So that is VF squared. So since we've got it already in our calculator, we're going to say square root of my last answer. We don't even need to type it in. That's how awesome this calculator is. And we get an answer there of 4.43 meters per second. Have we got any of those on the page?
4.43. Okay, so now what I need to do now, because obviously I need to keep things fair.
Absolutely.
Let me have a look. I can see a 4.43.
And wait a minute, let's just make this a little bit more tricky. This is a vector quantity. That means that it needs a direction to be correct.
You've got a minute to do it then. Can you do it in a minute?
Oh no, well this is done.
Oh, it's done.
All we needed to do was to say down and down at the end. Okay, remember that falling objects are going downwards, guys.
Down.
If you didn't give me an answer with a downwards, you haven't followed the first rule of vectors. They must have direction. So most of you are going, oh man, I forgot the direction. Please, 4.43 meters per second as we go down. Okay, so I hope that you guys answered that challenge question and you were able to see our physics live in action, but unfortunately we're starting to run out of time here, Indy.
Okay, so now what I'm going to tell you guys is that I'm going to look through the page. I have seen a few of you have said 4.43, but I do want to make sure that the right person gets and the first person who answered that answer gets it. So I'm going to go home, I'm going to go and have a look on the page, and I will be posting the name of the winner on the Facebook page. Let's say, give me some time at 8 p.m. I will be posting it. Thank you so much, Mindsetters. Grade 12s, don't forget that we've got spring school from the 1st until the 7th of October. You guys rock, and we're going to have so much fun. So make sure that you write that down in your diaries, and you also download the schedules as well as the spring school guides. And Liberty, you guys rock. You guys are amazing. You make the show possible. And all the Mindsetters out there are thanking you. Thank you. Thank you. Have an awesome evening, guys. Bye.